So let's do an example, and this will help us understand how to apply this in a real situation. Well, we'll probably just get far enough to set the problem up, and then we'll have to save it. You'll have to catch the rest of it on the lecture notes or the video. Okay, we have some geometry here. Let's say this geometry is symmetric. It's a plane wall. You have a center line here, and then both the left and the right-hand side are subjected to a relatively high heat transfer coefficient at ambient temperature T infinity. Right? And so this, let's say this is all occurring at time less than 0. Right? This is all sitting happily at steady state, and there's some thermal generation that's occurring inside the domain. And so what you would expect to see is a temperature profile that goes down here on the edges, goes up in the middle. It's symmetric, so it's going to be dt dx is 0. You get this kind of parabolic shape that's appearing in this problem. So that's what's happening before our whatever disturbance occurs. And then at time equals 0, we have these two conditions that change. So we have HF and G dot. So HF will go to, H bar F goes to, what do they go to? 100 watts per meter squared. And G dot goes to 0 watts per meter cubed. So we essentially turn off the whatever is causing the generation in this. Maybe it's a wire or something like that. We're just turning off that source. So we want to then understand, how does my temperature profile change as a function of time? All right, so let's go through this, get started on it. The first thing we're going to do is we need to solve for the steady state or the initial condition. It's not just as simple as saying T initial is a constant temperature. We actually need to solve for that initial condition. So we already know how to do that, right? This is just a steady state problem. So you go through that analysis, a control volume analysis, with the differential in the x direction. We end up with a ODE that is d squared t. We'll call that t steady state. Dx squared equals minus g dot triple prime over conductivity k. So that would just come out of our control volume analysis. We can solve this, and we end up, let's see, doing first integral is dTSS dx is equal to minus g dot triple prime over k times x plus c1, and then again would be t steady state is, let's see, minus g dot triple prime over 2k x squared plus c1x plus c2. So that's our steady state temperature profile. We need to then impose the boundary conditions to figure out what those unknown constants are. So boundary condition 1 is going to be the temperature dx at x equals 0, right at this this center line here. That's going to equal 0 because of symmetry. Okay, so then that becomes what? Minus g dot triple prime times 0 over k plus c1 equals 0. So we learn that c1 is equal to 0. That kind of makes sense, right? This is a linear profile here. So this problem's symmetric on both boundary conditions. We wouldn't expect there to be an underlying linear behavior. So c1 should be 0. C2, that's going to be looking at the outer wall. So C2 is conduction minus k dt dx at x equals L is equal to h bar f times t steady state at x equals L minus t infinity. Both of these would be times the area, but it's the same conduction area and convection area, so it cancels out. So we impose this boundary condition, and let's see, we get the following expression: minus g dot triple prime times L equals h bar f times the group of minus g dot triple prime L squared over 2k plus C2 plus T infinity. So we could go back and solve this for C2, right? That's what we want to go back and solve that for C2. We're out of time, so we won't do that. But this is the setup for the problem. So this is going to give us our steady state temperature profile. Next, we need to figure out how that's going to change as we change the conditions. So, thanks, everyone.